So hi everybody. Today the talk is about infinite categories, the notion of infinite category, and the speaker is Thomas. So Thomas,
Yeah,
you can.
thank you. Thank you for joining us in this third week. I would like to start with two kind of disclaimers. So I thought of employing a different strategy this time, namely to pause a little bit at the end of every frame so that everybody gets the chance to absorb the content of a frame and ask potential questions while everything is still visible. I must admit that I'm not sure if I'll be able to remember it every time, but I will do my best. The second thing is that I've decided not to do a summary of everything I said last time at the beginning, but rather I have sprinkled little reminders throughout the whole talk wherever certain things become relevant again. And I may have even overdone it a little bit. I hope it will be appreciated and not be considered annoying in any sense. Okay, so the outline of this talk will be as follows. We'll start by introducing the notion of infinity categories and talk a little bit about them. Next, we'll introduce the homotopy category of simplicial sets. And we will finish off with the homotopy category of infinity categories. Okay, so we begin with infinity categories. And we will start by remembering some stuff from last week. So last week we discussed Kant complexes, which vaguely resemble what we think of as infinity groupoids, but more importantly, you should think of these objects as corresponding to spaces. Kant complexes were defined as simplicial sets, which have fillers of all horns, but not necessarily unique ones. And towards the end of the talk of last week, we also discussed ordinary categories, where we characterized them as being the simplicial sets for which all inner horns admit unique fillers. Now, it is quite clear that Kant complexes are not ordinary categories, and ordinary categories are not Kant complexes. But we can, however, make these two notions marry, or said differently, we can introduce category theory in the study of Kant complexes by making the following definition. So this leads us to the definition of infinity categories. So we say a simplicial set C is an infinity category if all inner horns admit a not necessarily unique filler. Now in the literature, there exist also other names for this object. The infinity categories are also called weak Kant complexes for obvious reasons, but they're also called quasi-categories. Quasi-categories is the name which Joyal uses, whereas infinity categories is the name which Lurie has promoted and which I think is what most of the people are using. Okay, so we can check out some examples. There are some immediate and obvious ones, namely Kant complexes are infinity categories. And the nerve of ordinary categories are infinity categories. Then we have an example which we will revisit later, namely the fact that the collection of functors between infinity categories form again an infinity category. And finally, an example which is probably maybe the most important observation, which is that the collection of all Kant complexes forms an infinity category. Now, there exist also alternative perspectives or other approaches to formalizing the same notion. I will only briefly mention them. We will not discuss them any further in this talk, at least. So the first one is the topologically enriched categories. And we also have simplicity enriched categories. These two notions are mostly represented by Lurie, real, and verity. Then there are also Siegel categories and complete Siegel spaces, which are mostly studied by Resk. And finally, we also have A-infinity categories, to which I must admit I don't have a name which I can attach to. Okay, now next we move on to the notion of functors between infinity categories. So we define an infinity functor between infinity categories. Oh, sorry, I just realized I promised that I will pause between every frame. So are there any questions until this point?
So those alternative approaches that you mentioned on the last slide, are they alternative approaches for axiomatizing the infinity categories?
Hi, everyone. Can you hear me?
Yes, Thomas, I can hear you.
I think
I can also hear you.
Okay, so I dropped out. Okay, so it seems like my internet stopped for a moment, so I dropped out. I'm not sure what the last thing is you've heard. Do you get to hear this slide? Wilson?
Well, the question was easy. The different approximation model what? Infinite categories? Well, the question of Lucas. Or what are the different approximation that you explain?
Okay, sorry, I'm not sure if I could hear the question properly. Can everybody hear me actually? I'm
Yes.
still confused.
Yes.
Okay.
Yes.
So what was the question?
So my question was if those approaches can also serve to axiomatize infinity categories, or to what exactly are those approaches an alternative?
Okay, I must admit that I cannot say too much about these other approaches. I have a suspicion, but there is something I could say in general about also the definition of the infinity functors which we have above. But this will lead to quite some discussion, I suspect. So if you don't mind, I would prefer to postpone this question to the end of this talk. And I could share my current understanding.
Yes, okay, no problem.
Yes, if you want, and then I can help you with the answer of that question.
If I forget, please. Okay, but maybe we do it later.
Yes, and then if you want, I can help you with the answer. Okay, and also with the infinite categories if you want. Okay.
The connection is still bad, and I can't hear everything. Yeah. Okay, I can't hear everything you're saying. I will switch rooms, hoping that it will improve. I'm sorry for that.
Don't worry. Technical problems.
Okay, so hopefully things are better here. Okay, yeah, but please, if I forget, remind me at the end, because I think it is actually also an important question, and
Sure.
I think it's important to discuss it. Okay, so Next, we move on to the notion of functors between infinity categories. And we say an infinity functor between infinity categories is simply a natural transformation. For Kahn complexes, there's not much to say, but for ordinary categories, it may be interesting to know if this actually reduces to the notion of an ordinary functor. So this is what we will check next. So consider a infinity functor between ordinary categories x and y considered as simplicial sets. That is, if you consider the nerve of these categories. Now we haven't seen the proof last time of this equivalence, this characterization. So we'll briefly go through it here. The categorical structure is encoded in the simplicial set in the first three sets, namely x0, x1, and x2. Here, the zero simplices and the x0 should be thought of as the objects of the category. X1 is the set of the morphisms, and x2 is the set of all composable pairs. Now, the morphism D1 is the domain morphism, so it maps every morphism in X1 to its domain. Similarly, D0 is the codomain morphism. S0 maps every object to its identity morphism. And D1 upstairs is the composition morphism. And to see this, recall that every two simplex may be visualized as a triangle, as here on the right, where the left edge represents the composition of F with G. And indeed, this left face is computed as D1 of sigma. So we have the same thing for Y. And the existence of the natural transformation just delivers three morphisms, phi0, phi1, and phi2, which make all the corresponding squares commute. That is, it preserves the whole categorical structure, which in particular implies also that this is an ordinary functor. Okay, next. I can pause again. Okay, next we move on to natural transformations between infinity functors. But before we get there, I'll present a small warm-up. Maybe we'll consider the natural transformations in ordinary category theory. But recall that 1 here represents the category with two objects and one non-trivial morphism between them. So we can make the following proposition: let f and g be two ordinary functors between two ordinary categories C and D. Then we have the following two equivalent statements. Phi is a natural transformation between f and g. Also, big phi is a functor from the product of the category C with the category 1 into D, such that if we restrict phi to 0, then we get the functor f. If we restrict phi to 1, we get the functor g, as in the diagram here on the right. And if we restrict phi to an object C and the category C, then we get the corresponding component of the natural transformation for every object C in the category C. Now we want to translate this somehow into we want to formulate it in a way which will make it suitable for generalizing it to simplicial sets. And to do this, we'll recall that a category C can be represented as a simplicial set via the nerve functor. Are there any questions so far?
At the moment, no.
Okay, good. I will move on then. Okay, so we use the nerve construction. So for every category C, we can construct the corresponding infinity category, the nerve, which is just the functor represented by C. And if we apply this to the category 1, then we get the functor represented by 1, which by definition is the 1 simplex. So this suggests a definition for the case of infinity categories, namely we simply replace the category 1 and the previous frame by the 1 simplex here. So we make the following definition. Let psi and chi be two infinity functors between two infinity categories x and y. And a natural transformation, big phi, from psi to chi is an infinity functor of this form here, such that if we restrict it to 0, we get the infinity functor psi, while if we restrict it to 1, we get the infinity functor chi. Okay, we are now ready to describe the infinity category of infinity functors. So consider two infinity categories C and D. The infinity category of infinity functors is defined to be the simplicial set, which to each n delivers the set of infinity functors of this form, that is from the product of C with the n simplex into D. We can maybe gain some intuition by looking at the 0 simplices and the 1 simplices as examples. So the 0 simplices of this simplicial set, by definition, is the set of infinity functors of this form. But since the 0 simplex is just a point, or in particular it's the terminal object, this is the same thing as the set of infinity functors between C and D. So indeed, one may say that the objects of this infinity category are the infinity functors from C to D. Now at level 1, by definition, we have the home set of this form, which by the definition of natural transformations is exactly the set of all natural transformations between infinity functors. Okay, again, I will pause a little bit for questions. Okay, this completes the first section.
Yes.
See.
Can I ask a question? This is just the internal
Yes,
home
please.
in simplicial sets, no?
Yes, indeed. You're right. Yes, I must admit I hadn't noticed it, but it is exactly yes.
Okay, thank you.
Yeah, thank you for noting that. Are there any further questions? Okay, so we move on to the next section, namely the homotopy category of simplicial sets. So consider again the nerve of category C. This nerve turns out to be part of, it is the functor represented by C, and it turns out to be part of a functor from the category of small categories to the category of simplicial sets. And moreover, this functor has a left adjoint, little h. And little h applied to a simplicial set X is called the homotopy category of that simplicial set. In the literature, there exist also other names, such as the fundamental category. This latter name is motivated by the fact that the fundamental category of a singular simplicial set of a topological space is exactly the fundamental groupoid of that topological space. But we again follow Lurie's choice of names, which is homotopy category. Okay, so I would like to present a construction of this homotopy category. But before we get there, we'll go through some motivation again. So recall that for the nerve of a category, the two simplices are the set of functors of this form, which, as usual, we represent by these triangles. In particular, G may be computed as D0 of sigma, F is D2 of sigma, and Fg is D1 of sigma, which we think of as the composition. We also have the morphism S0 from 0 simplices to 1 simplices, which to each object deliver the 1 simplex corresponding to the identity morphism. It is the identity morphism in the sense that there exist two simplices, tau L and tau R, witnessing, so to say, the left and right unit laws for every 1 simplex F. Okay, now for the construction of the homotopy category, we will begin by defining a graph G. The set of 0 simplices will be the vertices of this graph, while the set of 1 simplices will be the edges of this graph. So this will in general look something like this. In particular, it will also include the faces of 2 simplices, and it will also contain the 1 simplices S0 of x for all 0 simplices x. Now this graph here has no reason to admit the structure of a category, that is, has no reason to be the underlying, actually directed graph of a category. And moreover, there is no reason for D0 sigma and D0 D2 of sigma to be in any sense the composites of D1 of sigma. But we can turn this graph into a category by applying the free construction. But we also want to imitate the what we've seen in the previous frame. Namely, we also want to impose certain relations, which are the composition and also the identity. That is, we want to interpret D1 of sigma as the composite of D0 sigma and D2 of sigma, and we want to interpret S0 of x as the identity. Now, to gain some intuition for what this free construction is doing, we can look at some examples. So given the following graph, where we have just 2 edges, F and G, if we consider the free category on this graph, then this will be the category which contains F and G as morphisms, but it will also contain all possible composites thereof. That is, it will contain also the composite G with F, it will also contain the composite GFG, and so on. Now, if we start with the same directed graph and consider again the free construction, but now additionally impose the following relations, namely we impose that G composed with F and F composed with G is the identity, then again we get a category containing F and G as morphisms, but that will be all, because this category contains the directed graph as a subgraph, and it also contains all the possible composites. So this process here may be compared to that of free monoids or free abelians. As a matter of fact, all free constructions in algebra Technically, they all satisfy the same universal property. And intuitively, you can think of it as follows. So what you're trying to do is, starting with a graph, you want to produce a category which is in some sense free of any additional constraints apart from the given relations which you ask for. This may be interpreted, if you wish, as a kind of a lower bound on the morphisms which the category must have. But at the same time, you want your category not to have any additional junk elements. It must be free of junk, so to say. And this imposes intuitively a kind of an upper bound. So in this sense, the free construction can be thought of a kind of optimization process where the free object is the universal solution to this optimization process. Okay, we now move on to some examples of the homotopy category. So the first one was already mentioned. If we start with the singular simplicial set of a topological space T, then the homotopy category of this simplicial set is exactly the fundamental groupoid. Another interesting example is taking the homotopy category of the n-simplex. This delivers the category n. And we may take this and plug this into the adjunction which we considered above. The adjunction between the homotopy category and the nerve of the category. And this will yield this equation here, which may be interpreted as a characterization of the nerve of a category. In particular, if we had started out with the homotopy category and asked if the homotopy category as a functor admits a right adjoint, then this right adjoint must satisfy this equation here. And by the Yoneda lemma, this completely determines actually this functor. And if you compare the first term and the third term, we actually recover exactly the very definition of the nerve of a category. Questions so far? Okay, we can now move on to some standard category theory mumbo jumbo. So since n is a right adjoint, it preserves limits. Now for the next observation, we will consider a category C, then apply the nerve construction to it, and then consider its homotopy category. If we think about this carefully, so if you take the nerve of a category, then the one simplices is exactly the set of all morphisms of that category which we started with. This means when we then construct the homotopy category, the graph which we start with is in fact the underlying graph of a category. And moreover, it is compatible with the relations which we impose. So if we take the homotopy category of the nerve of a category, then we end up where we started. And this is witnessed by the co-unit of this adjunction, which turns out to be an isomorphism. Now, the co-unit of an adjunction is an isomorphism if and only if the right adjoint is fully faithful. So as a corollary, we get that the nerve functor is fully faithful. And this allows us to interpret n as an embedding of the category of small categories into the category of simplicial sets. Okay, I'm assuming there are no questions. So recall from last time that we had a similar situation there, but with cat replaced by top. There we had the adjunction between the singular simplicial set S and the realization functor. But there we had noted that the co-unit is a homotopy equivalence if and only if the topological space T is homotopic to a CW complex. In particular, the co-unit is not an isomorphism, so S is not fully faithful, so we cannot play the same game here. So to say, we cannot, S does not deliver a embedding of top into simplicial sets. Okay, this completes the second section. So if there are any questions, please don't hesitate. Okay, so we move on to the homotopy category of infinity categories now, which admit an alternative description. So from now on, C will always denote an infinity category. And given this infinity category, we want to produce a category. So we do this by first doing the following definitions. For zero simplices x, x0, and x1, we define the Hom set for C of the zero simplices x0 and x1 to be the set of all one simplices f, of which the domain is x0 and the codomain is x1. Now in the Hom set of x to x, there exists a distinguished element, namely S0 of x, which we will denote by 1 subscript x. We will continue with the following definition. So given two one simplices f from x0 to x1, and another one simplex g from x1 to x2, and given also a two simplex of this form here, we will say that H is a composite of F and G. Notice that F here is not unique, since the existence of fillers of inner horns in infinity categories are not unique, which is why we say a composite of F and G. But we want to turn this data here into that of a category, and we do this by quotienting out by a certain equivalence relation, which is what we turn our attention to next. So we make the definition given to one simplices f and g, both from x0 to x1. We define the left homotopy between f and g to be a two simplex of this form. And similarly, we say a right homotopy from f to g is a two simplex of this form. Notice that here we switch g and f. Now there are two important observations we start with, which we put into a lemma. The first observation is that these two relations turn out to be equal, so we may as well just drop the subscript. And also, this relation is an equivalence relation of the Hom set from x0 to x1. We will use square brackets for the equivalence class, which we will call the homotopy class of F. Are there any questions? Okay, we will continue with a bunch of lemmas, which the proof of which all basically boil down to the filling out of certain 3 horns. So it is actually quite neat and a lot of fun to see how the formalism of simplicial sets actually captures this a notion of homotopy in this combinatorial way. But at the same time, I must admit that there's also a certain ugliness to it. If you look at what we define as homotopy, if we had a topological space, then F and G would be just like 2 paths, so to say, which have the without the existence of this one morphism there. So in some sense, there's a certain rigidity in the notion of simplicial sets, which forces us to consider these triangles instead of just F and G. So in order to fit homotopies into simplicial sets, we have to compromise a little bit, and this becomes even worse when you consider simplices of larger order. Okay, but I'll leave that comment aside. So the next important observation which we want to do is the following. Given F homotopic to F prime and G homotopic to G prime, given also H a composite of F and G, and H prime a composite of F prime and G prime, then H is homotopic to H prime. And what this is telling us is that given a situation as in this diagram here on the right, where H is a composite of F and G, then the composition defined on the homotopy classes of these edges is well defined. And this composition satisfies everything you want it to, namely it is associative and it satisfies the unit laws. Are there any questions? Okay, so basically what we have shown is that there is a category pi of C, of which the objects are the zero simplices of C, and the hom set is the quotient of the hom set of C .
Well, I think we have a technical problem again, so we will wait what happened with the connection of Thomas. Well, usually at this moment we have to put a song, but please, we have to wait. I don't know what happened with Thomas' connection. If somebody has a question, please do it. Yeah, and we will try to solve it.
Maybe, Wilson, you could answer the question that Lucas asked before.
Yeah, sure. Well, come back, Thomas. Hi, Thomas. Don't worry.
Hi, sorry, I disappeared again.
It's your connection. Don't worry. Sometimes happens.
Yeah, I'm not sure what the problem is, but okay, we're close to the end, so I hope we'll make it without any other disruptions. But maybe this was a good opportunity for people to think if there are any questions.
Well, the same question about the Lucas question. Try to solve that question. But we can talk about this one in 2 slides, so don't worry.
Very good. Okay. Okay, so we have this category pi of C, and one can, we call it again the homotopy category. And the choice of name is justified by the fact that for infinity categories, these two constructions are isomorphic. We can prove this either by using the universal property of the first construction, which delivers explicitly the isomorphism, or one can show that pi of C also admits the nerve functor as a right adjoint, and by the uniqueness of right adjoints, then these two objects must be isomorphic. Okay, so there's one more thing which I'd like to share with you, but for this we will need to introduce one more notion, namely that of isomorphisms. So a one simplex F is said to be an isomorphism if there exists another one simplex F minus 1, and there also exist two simplices S and tau, which are of the following form, as in these pictures here. So the left picture says that F is the left inverse, that F minus 1 is the left inverse, while the right two simplexes that F is also the right inverse of F. Now, if we have an isomorphism and we descend to the homotopy category, then we interpret these two simplices as actual composition. So what this is, what this says is that isomorphisms in the infinity categories become actual isomorphisms in the fundamental the homotopy categories. And the in Kant complexes, we've discussed that they were defined as those for which all horns admit fillers, and in particular this implies that every one simplex has an inverse. So every one simplex is an isomorphism in a Kant complex. And this is the first observation. And as already stated, every isomorphism in an infinity category descends to an isomorphism in the homotopy category. So we get the proposition that if C is a Kant complex, then the homotopy category is a groupoid. But in fact, the converse is also true. But I'm afraid that the proof is, I think, a combinatorial nightmare. But I think the statement is at least quite believable, because if we start with the homotopy category, and we assume that it is a groupoid, then this means that every morphism has an inverse, and by definition, this means that every one simplex in the given infinity category is an isomorphism. This means that for every one simplex, we can produce inverses which fit into the diagrams as depicted here. And one can then use these inverses in order to fill out all the necessary horns. All the horns for every level n. So this should be the intuition for the converse. And this completes my talk for today. So I'll finish off with a thank you for your attention. And I guess we can now proceed to the questions which have been raised. Are there any other comments before we do that?
Well, can you back to the slides, the previous slides, please?
Yes.
Well, it's like observation. In the 19th, Jojal's work tried to develop all the theory of quasi-categories, or in other words, infinite categories. So the problem was that he cannot prove the proposition that if C is a can complex if only if the homotopy category is a group point. So this proposition is an important tool in infinite categories. Why? Because with this proposition, we can to see that the infinite categories, the quasi-category, is a model of higher categories. Okay, so this is a very important proposition, and has said Thomas, is so technical and use a lot combinatorial stuff. A proof of this one in a easy way is in the book of elements of the reference of the seminar. We can
by Emily Real, right?
yes. So this is a very important proposition.
Mm-hmm. Good to know. Yeah, thank you for that comment. Mm-hmm. Okay,
Well,
if there are no...
I don't know if we start with solve the question of Luca. So
Yes.
please, can you go to the slide of the models?
Yes. Let's see, quickest way to get there. There we go.
Thanks. So I don't know if you want to say something or I can talk. I don't know.
So I have a feeling that there are two questions. So is it correct that there is a question about what exactly they are modeling and what is the difference between these different approaches? Is that correct? Are both questions to be addressed, or is only the second one actually?
I think so. Is the first one, Luca? Can you help me with that? Sorry, I forgot.
Yeah, both ones are interesting.
Okay, I agree. I can try to answer the first one. I cannot say much about the second one. There, maybe Wilson, you can then step in. But I can share my understanding regarding the first question. So, indeed, when we ask what are the infinity categories supposed to capture, what are they supposed to formalize, and my current understanding is as follows. The question which we're trying to answer is, or what we're trying to do is, we're trying to find a good home for homotopy types. That is, what we're actually trying to do here is homotopy theory. Is Joachim actually also here? Because it would be nice if he could then also confirm everything I say. And
no, I think so. Joachim say is a little unprecise this approximation, but just continue.
Okay, so yeah, my understanding is that what we actually want to do is do homotopy theory. What we're looking for is a good framework for homotopy types. The first observation on this path is that homotopy types may be identified with Kahn complexes. This is this follows from the adjunction which we have seen, namely that between the realization functor and the singular simplicial set, which will turn out to be an equivalence, equivalent equivalence, and reduce to an equivalence between homotopy types and Kahn complexes. So that's the first statement. Homotopy types are the same thing as Kahn complexes. And this was already realized quite a long time ago, I think, even already by Kahn and others. But the next important realization is that Kahn complexes, that the collection of Kahn complexes form a quasi-category, which we also call infinity categories here. And this is where everything really took off, as far as I understand, because by realizing that the collection of Kahn complexes form an infinity category or a quasi-category, you have at your disposal all the tools of infinity categories. And here an analogy would be the realization that the collection of sets form a category. And in fact, this analogy is quite strong in the sense that the Kahn complexes indeed do end up, from what I understand, playing the same role in quasi-categories as the category of sets do in ordinary category theory. In particular, a large part of the theory of ordinary categories can be generalized in a relatively direct way to the theory of quasi-categories. So in this sense, quasi-categories turn out to be much closer actually to one categories in some sense, more than they are to two categories actually. The theories are very similar. So this is a first hint that we can think of quasi-categories as a certain type of weak categories. Now, you may ask what justifies the usage of the names of infinity groupoids for Kahn complexes and infinity categories for quasi-categories. So I can give two explanations for this. The first is the fact that there do actually exist, from what I know, explicit constructions from scratch, so to say, of infinity groupoids. The relevant person here being Batanin. And there, from what I know is that there exist certain equivalents, certain Quillen equivalences, which identify these infinity groupoids of Batanin with the Kahn complexes. So this is one justification. And then there's a second justification, which comes from a theorem of Joyal. To understand this, it is one should first note that an n-simplex determines a set of an n-fold set of one-simplices, which I will call the spine of that n-simplex. Now, the theorem of Joyal says that the subset, or it's actually the space of all n-simplices with the same spine is a contractible space. And I interpret this statement as saying in some sense that all the n-simplices with the same spine are they are homotopic to each other. In particular, all the higher n cells are invertible using homotopies. So this also justifies the notion that there exist higher homotopies, so to say. Now I have to think for a moment how I want to.
So don't worry, if you want, I can tell the history about all this stuff in a chronology way, like a timeline. Can I help you?
Yes, of course, but give me a second. I just want to see if I managed to say everything which I wanted to say. Okay, yeah, there are a few things I'd like to say. So, in this sense, the infinity categories a la Lurie, from what I understand, are much more about homotopy actually than they are about climbing up the categorical ladder. And this is also why we say they are infinity one categories. That is, they are like ordinary categories. They have non-trivial morphisms at level 1, but we also remember that there exists a tower of homotopies living above this categorical layer. So this means that whenever you discover or realize that what you're working with actually admits higher homotopies, then the infinity categories will be a suitable framework. And this does not mean that this has nothing to do with higher categories. Indeed, higher categories, in the sense of climbing up the categorical ladder, also have a certain relevance. The most prominent example which I can think of is the work of Baez and Dolan in topological quantum field theories, where they work with cobordism categories. There, indeed, you consider n categories, but the point even there is also, again, remembering that there exists a tower of homotopies above the categorical layer, which goes on to infinity. And yeah, I think this is everything which I'd like to say regarding this question. I hope this somewhat clears up things a little bit. At least this is how I've managed to make sense out of everything so far for myself. Are there follow-up questions? Or maybe Wilson, you would like to also share your...
I think so. I have to organize your ideas. Okay. So
okay.
The notion of infinite categories is in the original idea of this notion is a technical tool in homotopy, as a Thomas, and algebraic structures. Okay, so the notion of infinite category was introduced by Borman and Vogt in their work on homotopy invariants. So the idea of they is no using category theory. Okay, so Joyal studied this notion, and in the 18th note that this notion can help you to understand the end connections in category theory, because in the 18th, 19th, one of the open problems and the principal problem in category theory was understand what is a n-simplex, what is a n-morphism, because at the level 2 is easy. We have categories, we have functors, natural transformation, and after that we have modifications. But in the next level, it's hard to define a connection in a categorical point of view. Okay? So, Joyals developed that the quasi-category notion, the infinite category notion, can be a model of the n-morphism. So he thinking the following: I can solve this problem, define an infinite version of the problem, and after I solve in an infinite way, I just truncate my notion, and that gives me the notion of n-morphism. That was the original idea of Joyal. Okay, so what happened with these alternative approximations? As I say, the principal problem at the beginning of this century in category theory is try to formalize the idea of AN categories. Okay, so in the case of phi, the A infinite categories are a model that use operands. Okay, but the person who know more about this stuff is Alex. So if Alex can help me about operas, will be great. Other alternative was the Siegel categories and the complete Siegel spaces. Okay, so 3, 4 again was created to solve a problem in algebraic geometry, not to solve something in category theory. Okay, so the original idea of Siegel spaces quasi-categories was always solve a problem of algebraic topology, algebraic geometry, but using tools of homotopy theory. Okay, so the idea of these notions is not category theory, but the category theory people know that all these notions can help you to develop the theory of higher categories, right? So the problem is what model choose, and that is an open question and an open problem at this moment in category theory. So I don't know if that I answered your question, Lucas.
Yes, I think this answered my question and also about 5 other questions that I didn't ask. So thank you very much. This is very interesting.
But I would also like to respond to that if nobody else wants to jump in before I do.
Somebody has a question? Please do it.
Can I ask a question? Oh, sorry, Guille. Please,
No, you first.
No, you first.
Okay. Can you go to 19 slide, please?
So cute that
okay.
conversation, Victor and Guille. So cute.
Okay, 1 second. It was 19.
Yes, I think.
Where was frame 19? 15, 16, 17, 18, 19. Okay.
I think that we cannot see your screen.
Oh, sorry, I forgot that. Okay. Sorry. I forgot that I removed that. Okay, so there we go. Is this the slide you were looking?
Yes. In the lemma, the second point implies the first one, isn't it? Because I think the left homotopy and right homotopy is just the same relation, just in reflexive way, because you only switch the F and G.
Okay,
I don't
yes.
know.
Well, you get symmetry.
Yes.
But do you get everything?
If you switch the
yes,
papers
of course, I got it.
F, G, and G,
yes,
you got the same. So I think the second
Indeed,
point.
yes.
Also, I have another question about this. If you define the homotopy using the identity in X1, you have the same relation or not? I mean, if you change the identity to F in the right homotopy, you get the same relation, or is another one?
So you want to exchange F and the identity.
Yes, in the right homotopy. So you have X0, FG, and in the opposite side, the identity in X1. In X1.
I think you get something completely different because the direction here is crucial, right? You want F and the G to be two morphisms with the same domain and codomain. If you replace...
Also, you get.
No, sorry, Thomas, that's wrong. It's the same. In the case of set, it's the same. In the case of infinite categories of the spaces, when we work in spaces, is a homotopy equivalent to relation. So, and the end is the same in a homotopical point of view. It is the same.
But wait, if I exchange F and the identity in the first triangle,
no, in the second one.
In the second one, you want to exchange F and the there, of course. Okay. Okay. Sorry. There. Okay. Yes, that I can believe, but not in the first one, right? In the first one, you get something different. Okay.
Yes,
sorry, I was
in the
looking
first
at
one
the
you
first.
have to chain with G.
Yes.
Can I say something? Just for the record.
Sure, Victor.
When you are defining the equivalence relation on the left or on the right, you are just saying that the composite is homotopy equivalent to F composed with the identity on the right or with the identity on the left, and just they are just the two notion of left homotopy or right homotopy.
I guess you can interpret it that way, yes.
So if you want change, as Wilson said, F with the identity, the one on the left of the right hand side, you are just saying that you are defining the left homotopy relation, interchanging the roles of G and F.
Okay.
Sorry, I lost you a bit.
Maybe I make it a little.
But other observation for everybody, this stuff is important. Why? Because in model categories, we have a huge problem, because in category theory, usually we cannot define a good notion of homotopy. What is homotopy between two morphisms? Okay, when we think in topological space, it's easy. In simplicial sets, it's easy also too. But in a general category, it's complicated. That is the reason the people work in model categories, because it's the best way to do homotopy theory in category theory. Okay, but when they develop of this theory, all the people know that the more easy way to do homotopy in category theory is infinite category quasi-categories. Okay, so this is a very, very nice model, but it's a special case of a model category. Okay, and we use a lot of tools of model categories, but only emphasize in simplicial set topological spaces, and that's all. So all this is a special case for model categories, but is the important of this theory. All this stuff do the help us to do homotopy theory in category theory in higher categories in a more easy, clean, and precisely way than model categories.
Yeah, this is also my understanding, indeed, that the infinity categories serve as at least as a kind of a replacement also for model categories. Model categories were also an attempt somehow to become a suitable framework for homotopy theory, but it is somehow a highly technical and ad hoc language, from what I understand. And the infinity categories, they are a much more suitable language.
Yes, most
Actually,
active.
for doing.
Yes. Victor, I think so. You have another question, I think so, because you have a cute conversation with Guille, but I think so you also have a question.
Yeah, I was asking myself, Thomas' comment that the notion of isomorphism in an infinity category is reduced to being an isomorphism in the homotopy category. And that's all the content of the Joyal theorem. And then you said, Wilson, that in Reel's book, with Verity, this is proven in a more clear way, maybe?
Yes, because she and he, because are two the co-authors, do only the elements. We need to do that proof because that is so technical. But it's natural because they published the book 2 years ago, but Georgia proved this 20 years ago. Okay, so if somebody wants to understand the construction, it's more easy to read Emily books than the original work of Jojo.
Yeah, my question is not that the Joyal work is not valuable. My question is, if you know, what's the point of the proof of Real and Verity?
Unfortunately not. I checked it out, but it also, I think, from what I've seen, is I think they also work in the more general setting where the simplicial sets have additional structure of some so-called markings. So yeah, I don't know. Maybe you, Wilson, had a look at the proof. I must admit it.
Yes, but I never understand the technical details. It's appendix of the book. It's hard.
Yes.
I only can
I mean,
say
they
that
also defer it. Yeah, and
Okay,
unfortunately, yeah, no problem. But unfortunately, if I understood it correctly, they don't do it simply for the case of just plain old infinity categories, but rather they do it for the case with this additional structure. So
for an infinite topic, it's a little more general.
I see. Okay, so the markings
are more general because infinite topos is the more general structure to define a higher category. So the infinite categories in our case is a special case of topos, okay? The Siegel spaces is a special case of infinite topos. So that is a more general theory.
Wilson, you are saying that the infinity category of infinity categories is a topos?
No.
That's not right.
No. Infinite cosmos, Victor. The infinite cosmos is a more general structure to define higher categories. A special case is the infinite categories, okay? So an infinite cosmos is
you are saying that something different. For an infinity cosmos, they prove their result.
Yes.
Okay. I understood that they prove it for infinity topos. And
No. That is stupid. I'm sorry. If I talk in a wrong way, so sorry. No, it's false. It's their proof to infinite cosmos. So somebody has more question, or is we can finish the talk?
Yeah, I'm not sure if everybody is still interested or already sick of this, but I would actually like to respond to your take, so to say, your remarks on the motivation and the history, so to say.
Yeah, sure. We can talk about this in more in details the next session if you want, because when we continue study this notion, maybe all our questions are solved in the work. So
Okay, as you wish. Okay, we can also postpone it if you prefer.
So thanks to everybody to be here. Thanks to do question, listen to us, and I hope you like this talk and the idea of the seminary. So I will see the next week with the mapping space of this stuff. And thanks again, and thanks to Thomas. Really, thanks, Thomas.